Have you ever stopped to think about the invisible safety net that holds our entire digital world together? Every time you check your bank balance or add something to an online cart, there's this powerful set of rules in the background making sure all that data is reliable and safe. Well, today, we're going to pull back that curtain and see exactly how it all works.
Okay, just imagine this for a second. It's a total nightmare scenario. You send a friend $100. You see the money leave your account, but before it ever gets to theirs, it just disappears. Poof, gone, lost, somewhere out there in the digital ether. It's a terrifying thought, right? And it's the exact problem that had to be solved to make things like online banking even possible.
Because a transfer that seems so simple is actually, well, incredibly fragile. It's just two little steps. But what happens if the system crashes right after step one? Your account is down $100, but your friend's account hasn't changed. The money is just stuck. It's effectively lost in limbo. This built-in weakness is what we call a fragile transaction. Any little interruption, a network hiccup, a power outage, you name it, could leave our data in this messy, corrupted, totally inconsistent state. So how on earth do we protect against this chaos?
Well, we protect it with something called the ACID model. Now, this isn't a single piece of tech. Think of it more like a philosophy, a set of 4 guarantees or promises that database systems have to uphold. These 4 properties are pretty much the bedrock of reliable data.
The easiest way to think about ACID is like an unbreakable contract for your data. Seriously, every time you book a flight, buy something online, or send money, this set of guarantees is working behind the scenes, making absolutely sure that action completes correctly and safely.
All right, so let's break this down. We're going to start with our first 2 properties, atomicity and consistency. These 2 are all about the transaction itself, making sure it plays by its own rules and finishes as one single logical unit.
First up, we have atomicity. This is the all-or-nothing guarantee, and it is crucial. In our bank transfer example, this means both steps, taking money from your account and putting it in your friend's account, have to succeed. If that second step fails for any reason at all, the entire thing is just canceled. The system rolls it back like it never even started. And that $100, it's instantly back in your account. No more vanishing money.
Next up is consistency, which you can think of as the rule follower. This makes sure that any transaction respects all the predefined rules of the system. For instance, a bank has a very important rule. Account balances cannot go negative. Well, consistency is what enforces that. Any transaction that tries to break that rule, say by withdrawing more money than you have, is simply rejected. The database is never, ever left in an invalid state.
So here's the key difference between the 2. Atomicity is all about the process. The whole operation succeeds or it fails as one single piece. Consistency, on the other hand, is about the result, making sure the outcome is valid and doesn't break any rules.
Okay, so we've handled the internal logic, but what about the outside world? Let's look at how ACID protects transactions from other interferences and system failures with the next 2 principles: isolation and durability.
Isolation is so important in a world where millions of things are happening all at once. It guarantees that even if 2 transactions are running at the exact same time, they can't see each other's messy, halfway done work. It's like each one gets its own private bubble. So if you check your balance while a deposit is happening, isolation makes sure you either see the balance before the deposit or after it's totally done. Never some weird in-between number.
And finally, we have durability. This is the ultimate promise. It means that once the system gives you the thumbs up, once you see that confirmation screen, that change is permanent. It's written down in a way that'll survive a power outage, a server crash, pretty much anything. Your data is safe, forever.
So, to put it simply, isolation gives each transaction that private bubble to work in, so you don't have chaos from things happening at the same time. And durability basically carves the successful result into stone, protecting it from any future disaster.
So now that we understand all 4 pillars, let's just step back for a second and see why this model, which is actually almost 50 years old, is still so incredibly important in all of our modern technology.
So let's put it all together one more time. Atomicity gives us that all-or-nothing execution. Consistency makes sure the data states are always valid. Isolation stops different operations from interfering with each other. And durability makes the results permanent. See how they all work together? They create this fortress of reliability around our most important data.
And hey, if you want a really easy way to remember all this, just think of the letters. A is for all or nothing. C is for constraints are respected.
I is for independent execution, and D is for data that's saved forever. It's just a handy little trick to keep these core ideas straight.
And look, this isn't just some abstract theory for banks. Every single time you buy something online, book a seat on a plane, or even just update your social media profile, you are relying on these asset guarantees. It's the silent, reliable engine that's powering the digital services we all use every single day. And that brings us to a final, really interesting thought. Providing these 4 guarantees takes a lot of work for a database, and all that work can sometimes slow things down. So in a world that is constantly demanding more speed and massive scale, we have to ask the question, are these absolute guarantees of reliability always worth the cost to performance? And that right there is the central trade-off that developers and engineers have to grapple with every single day.